This meeting is being recorded.
In this next video from chapter 17 on some additional aspects of aqueous equilibria, we'll look at the last video about titrations. And these are just some bits of information that we might have missed along the way. So one thing to note, when we have a titration, and the equivalence point is going to be less than 7, using the acid-base indicator, such as phenolphthalein, would not be a good idea because that has this range up here between 8 to 10, where we see that color change occur. So that wouldn't be helpful because our equivalence point is down here. So if we used a different indicator, such as methyl red, that's indicated here. It's red in acidic conditions, it's yellow in basic conditions. So at the equivalence point here, which is less than 7, we see it around 5 somewhere. We can use an indicator that has this color change interval between 4.2 and 6.0, so that would fit well. So methyl red would be an indicator of choice here. So that's just to show that sometimes not every titration will use the same acid-base color change indicator. Another aspect of these aqueous equilibria that we want to look at is with titrations of polyprotic acid. So that graph is over here on the right, and we can see our species above the graph with three protons, all 3 protons on the left here, and then we only have 1 remaining proton here on the right. So what we see is that each equivalence point for each dissociation with a polyprotic acid. When we do a titration, we're going to see these separate equivalence points. So this is the first acid dissociation, this would be the second acidic proton dissociation, and so on. So that's good to note. If you ever see a titration curve that looks like this, it's in case of this, it's at least a diprotic acid, but we're shown here that it was a triprotic. So the last portion of this worksheet here that I wanted to review is a summary of what we might encounter with acid-base titrations. So what we're shown down here, what I had shown was a titration graph with different points along the way. So let me try to put this back where it was. All right, that looks pretty good. So let's take a look here. So we have over here a scenario with a strong acid and a strong base. So ahead of time, I drew our titration curve, which shows our pH on the y-axis. We have our volume of base as our x-axis, and we have some different points along the way for the strong acid, strong base titration. When we're at point 1, that's our starting point here. We have not added any base yet, so it's only the acid that we have to consider when we calculate pH. And we know with a strong acid, the hydronium ion concentration is equal to the concentration of the strong acid. So to solve for pH, we just take the negative log of that acid concentration. Then we move along, we start adding some base in this region 2 here. So we still have excess acid. We haven't reached our equivalence point yet. So we use, we do our calculation, we figure out how much excess acid is available, and then we plug that in here and solve for pH that way. When we get to our equivalence point, we cannot do a calculation here. When our moles of acid are equal to moles of base, our table, everything will zero out. So we end up just knowing that with a strong acid, strong base, our pH will always be 7.0 at our equivalence point. And then, so that was here. This dot here is our equivalence point at exactly 7. And then our last region up top here, that's when we have excess base. So we could solve for POH once we find our concentration of hydroxide ions. Then we take the negative log of that, get POH, and then 14 minus POH will give us pH here. So that's the last equation for a strong acid, strong base, and these 4 different points along the titration, what to use when. Then we see over here on the right, we see our summary of a weak acid, strong base titration. So now I have my 4 points. You'll see that my pH of 7 is below my equivalence point now at 0.3. So when we are at 0.1 here, we have a weak acid, so we're going to use a weak acid ice table. We will solve for our hydronium ion concentration. Let's move over a little here. And then that's by solving for X in our ice table. And then we plug that in to the negative log for solving for pH. So that's our step 1 here. You have to do the ice table first and then plug in to the same equation as with the strong acid, strong base. And then in part 2, or in region 2, we start adding some base, our titrant here. In this region, we're considered in the buffer region, and we have to use the Henderson-Hasselbalch equation, which I'm going to rewrite it up here because it got a little smushed down there. So we have our pH is equal to the pKa. So our weak acid, we take the negative log of the Ka, and then we add to that the log of the concentration of base divided by the concentration of acid. So that's the Henderson-Hasselbalch, and again, that's for part 2. When we get to part 3, the equivalence point, now we need to use that special case with the weak base ice table. So we need to, if we're given a Ka, solve for Kb using Kw, that's what's on top there. So Kw by Ka gives us Kb. We'll use that to set up our Kb expression. Solve for X, that would be hydroxide ions in this weak base ice table scenario. So we can first solve for POH. Then from there, we hop over here and we see that we have to the right 14 minus POH indicated. So that is how we would solve for pH here. So just 14 minus whatever POH value. And then once we get to 0.4, we are in excess base location again. So we're going to have to solve for our hydroxide ion concentration, find our POH, and then from there, 14 minus POH will give us our pH.